spilled my drink.
All right. So I have extended the homework today to being due at midnight. I figured you all could use some pressure relief, and I will admit just having a little bit of fun writing that email.
How long did it take you to write it? In all
Not
honesty.
that long.
In all honesty, though, like
Not that long, like 5 or 10 minutes, you know.
that's fair.
I mean, you gotta understand, I've been coming up with these puns for like 12 years, you know, so.
You mean you know how to teach fluids and you don't want
I
to?
know, I do not want to teach fluids,
In his
and I do not know how to
In
teach
his words,
fluids.
I don't know fluids, proceeds to use all of the fluid terms in an email.
Do you want me to quote something like exactly? Hell no.
All right, settle down, everybody. Settle down, settle down. We're in the land of solid mechanics right now, not fluid mechanics. So this is the land of structural analysis. Okay, everybody. In all seriousness, just some housekeeping items. So all of the outstanding homeworks are graded. Homework 6.2 is obviously due today at midnight. Still working on project 1 submittal, but I should have that done probably by Monday because I want to have that done. My goal is I want to give you submittal 2 after we've talked about math hand, okay? Because I think that's the best time to give you the submittal 2 assignment. So you can't really start submittal 2 until math hand. Math hand will be like a Wednesday, it'll be a Wednesday and Friday topic of next week. So Monday, we celebrate next week, and then Wednesday and Friday, we're going to be doing structural analysis using software, and the package is math hand. So homework 6.3 and 6.4 are due on Friday. Now 6.3, that's just installing the software. 6.4 is a frame analysis, which is what we're going to talk about today. To be honest, if you remember shear and moment diagrams for frames, remember how it wasn't really any different for beams? It's kind of the same story here. We're going to do that today, and I want to have a little discussion on the presence of shear deformations. I kind of like to close deflections with talking about shear, but we'll get to that here in a bit. Everybody get the code? Okay. Hold on. There we go. I didn't break out the mouse, so just use my hand. Okay. All right. So let's just make sure we're on the same page, that we've shaken off all the turbulence from the past hour and a half, and we're in the land of solid mechanics. We're talking about deflections, and so I want to just say one thing about this slide. So I have here that I'm recalling the virtual work for beam deflections, but I guess a more precise term for this would be virtual work for flexural deformations, okay? Because we can use this formula for frames as well, okay? But specifically what we're doing is we're computing deflections with this formula considering only flexural deformations, okay? And I'll explain what that means here in a bit. But we use the same approach, you know, for frames as we do for beams. We have our real moment function, our virtual moment function, we have our E and I, and we have our unit conversion factors. Same story for frames as it is for beams. But the story for frames is a little bit larger than this. And I want to have a more generalized discussion regarding the method of virtual work. So if we're talking about beams and in this case frames, so far we've only considered the deflections due to flexural effects. Okay, and what I mean by that is we're only considering the how the bending moments affect deformation. Okay, but it is possible that the axial loads affect deformation. It's possible that the shears affect deformation, etc. Okay, and so if you wanted to generalize the expression of virtual work, really it would be this. Okay, and I know this is kind of nuts here in terms of the size of the formula, but I'd like to sort of just like break down what we're seeing here. I want to be clear, everybody. I'm not going to expect everybody to do a problem like this, you know, in this course, but I just want to sort of like take stock of what this is saying. Okay. So let's say, for instance, that I have some sort of structural element in my hand, and I take that element and I stretch it, and I bend it, and I shear it, and I twist it, and I heat it up, etc. Okay? How do I compute the total deformation of point A from beginning to end? Well, it's however much energy the element is storing in response to the axial loads, however much energy the element is storing in response to the flexural loads, however much energy is response to the torsional deformation, etc. Okay? Now, if you look at these expressions, these should be pretty familiar. For instance, remember in Engineering 216, if you wanted to find the angle of twist, if you had an element you were twisting it, the angle of twist is TL over GJ, right? Well, I propose that if you wanted to find the deflections using virtual work, just have a little virtual torsion, a real torsion over GJ and integrate. Same concept. It's the same idea. I'm just expanding it. Okay. What I propose is that the more general expression of virtual work that you can apply to any structural system is this, and all you do is only consider the effects that are relevant to the system at hand. So, for example, if we're talking about trusses, we would never consider, this component, for example, or this component, etc., because for trusses, we don't have any bending moments, we don't have any shears, we don't have any torsion. Remember the assumptions that we make regarding truss analysis, that there's no friction, the loads are applied at the joints, the members are connected at a single point by their centroidal axes. We make those assumptions to state that axial forces are really all we need to deal with. We could talk about if truss members get longer or shorter, if they get hotter or colder, but essentially we're able to disregard a lot of the potential impacts, okay? So for trusses, we've only considered the axial deformation, okay? So if we were talking about a frame, okay, if we were looking at frame deflections, and really, we could talk about this with beams as well. Beams and frames could see bending moments, they could see axial forces, and they could see shears, okay? Now, for the sake of our discussion here and the problem we're about to do, I'm going to ignore shear deformations, but I'm going to talk about shear deformations a little bit later and talk about where they would be applicable. They're really not that hard to compute. If you can write a virtual and real moment function, you can write a virtual and real shear function. If you can do this, you can do that. It's not any more difficult, but I want to have a more relevant discussion as to why you would consider shear deformations. We'll talk about that here in a bit. Now, how do we do frame deflections? Well, it's the same idea. We do a real structural analysis, we do a virtual structural analysis, we put the load where we're interested in finding deflections, at the point of interest, in the assumed direction with a magnitude of 1, and write our functions. Now, in the case of the frame that we're about to do, we are going to consider axial deformation, and we're going to consider flexural deformation. But I propose that for frames, you can neglect axial effects. Okay, I'm going to explain that really with this example. Okay, so this is going to be the main star of the show today. So we're going to compute the deflection at point A. We're going to compute the vertical deflection using virtual work. Okay, now I'm giving you the real structure. We're going to consider flexural deformations, and we're going to consider axial and flexural deformations. So for this problem, we're going to need big M, big F. We're going to need little m, little f. We're going to need both for the entire problem, okay? So we're going to sort of do both, but you're going to see something that happens as we get to the very end. Now, the one thing I do want to say about this this situation, or this problem, is I want to talk. Something I haven't really discussed, I've just sort of taken it at face value, but I kind of want to discuss, are these properties right here, okay? So I'm giving you a Young's modulus of 30,000 KSI, and I'm giving you an area of 4 square inches and an I value of 800 inches to the 4th, okay? What I want to just say right on the onset before we do this problem is when it comes to the A value and the I value, the A is the cross-sectional area. Like if I were to lightsaber through the section, the area, that's how many square inches of area there is. And then the 800 inches to the 4th, that is the moment of inertia. So like if you remember from a rectangle, BH cubed over 12, remember that? So what I'll say about this cross-section is these values are a little bit unrealistic on purpose. For this area, this is a really, really big moment of inertia. Like what I'm saying is this frame, these members, are really flimsy axially. They have a really, really small area, okay? And so think that through. If the area is really small, they should stretch a lot axially, like along their axis. They should be like a rubber band. They should be like taffy, okay? But when we see how the numbers play out, you'll sort of get what I'm talking about, and how in most frame problems, we can neglect axial deformations. And the best way of explaining it is to just do the problem, okay? All right, so, okay. So, here's the structure. Okay, what I'm going to do is I'm going to redraw this structure, and I'm going to do it on two sides. So we're only going to do a vertical deflection. So the real structure and the virtual structure. Okay, so the real structure and the virtual structure, right? So the real structure is going to look like this. Okay, we have a distributed load. Of 3 kips per foot. Okay, we were given a horizontal load of 20 kips, a vertical load of 10 kips. Okay. Let me ask you a question. Would you trust me if I just told you what the reactions are at this fixed support? Like, would you believe me if I said that the vertical reaction was 70 kips, the horizontal reaction was 20 kips, and the moment reaction was 600 foot kips? And by the way, in terms of dimensions, this is 10 foot, this is 20 foot. And let me label this. This is A, B, C. Okay. Would you all agree with that? Is that okay? I mean, think you've got 20 to the left, so you got to have 20 right. You've got 10 down, 3 times 20 is 60 down, so 70 down, you got to have 70 up, etc. Is that okay? Okay, that's the real structure. The virtual structure is going to look like this. Okay, so the virtual structure is going to be very much the same frame. Well, I mean exactly the same frame, just no loads present on it. I've got a virtual load. I'm going to assume it deflects downward. I think that kind of makes sense, that it's going to go downward. This is A, B, C, 10 foot. Actually, let me put that down here. All right, and then for my reactions, 1, and this is a moment reaction, and it ends up being 20. Well, 20 foot, if we're being precise. Okay, so these are the two structures I'm going to have to analyze, the real structure over here, the virtual structure over here. Is everybody okay with that? Okay. Now, here's what I'm going to do, okay? I have two members, member AB and member BC, okay? So what I'm going to do is I'm going to define a coordinate system for member AB. We'll call this X1, Y1. So in other words, like the X-axis along the member, the Y-axis like that. So if I do that, I'm going to put the same coordinate system over here. Okay. And I'm going to violate my advice a little bit with the frame. I think it's going to be a little bit easier to write my function like this. Sorry, y2, x2. And the reason why is, like if I'm looking at this member, like neither of these are free ends. So where am I going to place the origin? Do I place it here or do I place it here? I'm going to propose placing it at C, because to place it at B means I've got to cut a section right here and do some additional equilibrium in order to figure out the unknown forces and moment right here. Whereas here I already know what they are because I've got the reaction. So I'm going to define my coordinate system like that. So the same thing over here. So it might, I guess a better way of saying it is, it might seem like I'm violating my advice a little bit, but I'm sort of not, because I already know what those are. Okay? So how many moment functions am I going to need to fully define this moment diagram along member AB? Just one, right? Because there's no loads from A to B. And the same thing's true over here. And for member BC, only one moment function, only one moment function. So that means I'm going to need to cut two sections. So I'll cut a section here, cut a section, I don't know, right here, cut a section right here, cut a section right there. Okay. Does that make sense? Everybody with me on that? Okay. All right. So here's what I'm getting at, and I'm going to use just the board for this, okay? Okay? So for the virtual structure, what I need is, I need like an FAB and MAB, and I need a those, right? I need to get the real, the virtual forces and the virtual moments. And likewise over here, I need this. Okay. Does that make sense? So I got to figure out these quantities. Okay? Now I'm going to do something a little uncharacteristic. Okay? I'm going to start with the virtual structure. I have a very specific reason why I'm going to start with the virtual structure that will become clear a little bit later. Okay? So what I'm going to do for the virtual structure is I'm going to do section 1-1 looking down, section 2-2 looking to the right. Is everybody okay with that? Okay, so let's look at this. So if I look at section 1-1 looking down, okay, what do I have? I just have this. Section 2-2 looking to the right, I just have that. So let's see what they look like. Okay, so section 1-1 looking down is going to be like this. It's going to be like that. I've got 1.0 going down. I cut a section at some arbitrary distance, which we'll call that arbitrary distance x1. Okay, and so this is point A. What are the unknowns here? Do I have any unknown horizontal forces right here? Like if I sum forces in the x direction, what's the horizontal force right here? 0, right? I do have a vertical force. I am going to have that. How much is the vertical force going to be? How much is that going to be? 1. Okay, so we'll put that here. How much is the moment going to be? How much moment is present in this member? It's not a trick question, by the way. If I have a member and I'm yanking on it, is there any moment present? No, so the moment is 0. Okay? So what I'll say is FAB is 1, MAB is 0. Those are from 0 to 10. Does everybody see why they're from 0 to 10? Everybody understand that? Because the member's 10 foot long? So far, so good? All right. So let's see if we can come up with something similar. Okay, so FAB, MAB for the real structure. Okay, so let's do the real structure. Okay, so what does the real structure look like if I cut a section and look down? Okay, if I cut a section and look down, what does it look like? I really came close to using the Expo marker on my surface just now. I really almost did. That would have been funny. Well, in retrospect, right now it would have been a little frustrating. Okay, so here's the structure. I have 20 kips, 10 kips. This is X1. Okay. So what I need is an FAB and an MAB. Okay. Let's reason through this. Let's start off with FAB. How much is FAB? How much is the axial force along the force of the member? Like, is the member experiencing tension or compression? Tension. And how much? 10 kips. Okay, so this is plus 10 from 0 to 10. So in other words, there is this. Okay? Now, I propose there is a moment present. Okay? So we'll call this plus 10 for the axial force. Does anybody know how much the moment is? 20x1. That is correct. That is not what I'm going to write down. What I'm going to write down is from 0 to 10. Why am I doing that?
You multiply it by the virtual moment, it'll be 0.
Exactly, because ultimately what I'm going to have to do is integrate from 0 to 10 this times this over EI from 0 to 10, right? It doesn't matter what this is. We're talking about strategy here, folks. I'm lazy. I don't want to have to do math I don't have to do. Does it really matter what this is when ultimately I'm going to multiply it times 0 and then integrate? This integral is going to go to 0. So it doesn't matter, okay? Does that make sense? That's why I don't really care. Have you ever had an engineering professor write a formula that says, who cares? Well, there you go. First time for everything, right? So, okay, does it make sense why I did the virtual structure first? Because recognizing that this is 0 meant I didn't have to do this work. This seems like an easier structure to deal with first. So I said, let's go ahead and do this first. Like, one of the things that you might be noticing on your homework that's due at midnight to relieve some pressure is that there are certain regions, let's say on the virtual structure, where the moment is 0. So why take the effort to derive the real function? Because you're ultimately multiplying it by 0. Does that make sense? Something to think about. Okay. All right. Let's do section 2.2, and I'm going to do the virtual structure first. Now I'm going to look to the right. Okay. So let's just sort of refresh. What does the virtual structure look like? So if I'm cutting a section and looking this way, I'm going to see this force and that moment. Okay? All right. So maybe what I'll do is, just to have a little reference here on the board, let's do this. So I'm going to have FBC equals something, MBC equals something. And they're going to be valid from 0 to 20. So let's see if I can fill that in. Okay. All right. So we've got my structure like this. Here's my section cut right there. I have a reaction of 1.0, a moment of 20 feet. Okay? So let's see. This is point C. This distance, we're going to call this X, or X2 in this case. Okay. Excuse me. So let's start off with unknowns. Is there any unknown in the X direction? There's no unknowns in the X direction. So what is FBC? What is this? Along the axis. So remember, little f is along the axis of the member. This is the stretching force, right? This is either stretching or squishing along the axis. This is going to be 0. Does that make sense? So before we do anything, what can you tell me about over here? What's going to happen over here?
Doesn't matter.
What doesn't matter?
FBC.
FBC. So we already know, we don't have to worry about that, okay? We just don't have to worry about it. We do need to get an MBC, though, for both sides. We are going to need to do that. And that's going to take a little bit of work. Okay. So, as for the moment, so just so we're aware, there is going to be a shear, and there is a moment. So this is moment BC, this is shear BC. And we could derive an expression for shear BC if we cared about it. We just don't care about it for this problem. We could care about it, and there are reasons why we might, but for this problem, we just don't. Okay? So I'm just going to sum moments at the cut. Okay? So I'm going to have MBC going like that, 20 going like that, 1 times X2 going like that. Okay. Is that okay? Does that make sense? Yes.
I have a question about, like, for the little FBC.
Yes.
Why is that not, like, 1 going down? Is it?
So, oh, you're talking about this.
Yes.
Okay, that's a great question. Let's talk about that. Okay, so if you cut a section in general, here, let's, if you cut a section, right, and look to the left, this is positive shear, this is positive moment. If you cut a section and look to the right, positive shear, positive moment. Okay? So to answer your question, here's what I would say. If we were summing forces in the y direction, what I'm saying is that that is negative. That's what I'm saying. So it is going down, right? But when you're deriving expressions for shear and moment, what you do is you automatically put, like this is always the sign convention if you cut a section, look that way. So we're cutting a section looking to the right, up and over. What'll happen, like, so if we were doing this, if we were doing summing forces in the y direction, all right, we would get VBC 1.0 and we would get that. Does that make sense?
Yeah, and then also, how is that 0 for FBC?
Great question. Okay, so let's go through that. So FBC, if I wanted to assume worst case positive tension, would look like that, right? So if I sum forces in the x direction, is there anything horizontal? No. So that's where I'm getting FBC is 0. It's great. Those are good questions. Did that make sense to everybody else? This is good stuff. I like that. Everybody good? So to summarize for this problem, I'm going to leave this here. This is good stuff. I'm going to say that FBC is 0 and MBC is x2 minus 20. Okay? And I'm actually going to address something else because you indirectly brought up another point. Okay. Does anybody notice how this fails the derivative test? Like if I take the what if I take the derivative of this, what do I get? I get 1, right? But this is minus 1. Why? Why is the sign flipped? The reason the sign's flipped is because the axis is going that way. The axis is flipped, so the sign's going to be off. So that was good stuff. Okay, so this is x2 minus 20. Yes?
How do you do 0 to 20?
Oh, yes, you're right. Thank you. Zero to 20. Yes, that's right. 0 to 20, 0 to 20. Okay. Everybody with me on this? Okay. All right. So the only thing we have left to do is section 2.2 on the real So section 2.2 for the real structure. A little bit more going on with this one. So because we've got to account for like all this, we got to do all this, cut a section look to the right. We have all this we have to deal with. So just a little bit more. So we have a 70 kip, we have a 20 kip, 600-foot kip, 3 kip per foot load. There's the section. X2. Okay. So what are my unknowns there at the end? I'm going to have an F, an axial force, and unknown shear, and a moment. Okay? Now we've already decided that FBC we don't care about because we're ultimately multiplying it times 0. Does that make sense? Everybody okay with that? Okay. All right. So what do we do with all this? Okay, well what we do is we collapse this into a point load, moment arm right here, and then we sum moments at the cut, right? So, when we sum moments at the cut, I don't need to consider that and that because they're going right through it. I'm going to have, let's see, I'm going to have an MBC on this side. I'm going to have 3x times x over 2. And I've got to deal with that 600. And that's going to be opposed by the 70 on that side. So unfortunately, this equation is just going to be a little messy. Not really anything I can do about it. So MBC plus 1.5 x squared plus 600 equals 70x2. So therefore, what do we have? We have FBC is who cares? And we have MBC is 70x2 minus 1.5 x2 squared minus 600. Both of these from 0 to 20. Okay. Yes.
Sorry, why is like is it my moments are like flipped? Is it because of the axis?
I'm sorry, what?
Like for NBC, I have it on the other side of the table.
Well, I have. Oh, that's because I made a boo-boo.
Oh, okay.
That's my fault. I needed to draw it like that.
Oh, okay.
I made a boo-boo. That was a whoopsie. It needed to be drawn up. That's the positive sign convention. It needed to match.
Well, would the point load moment be opposing the 600?
It is. That's why I have the 600 this side, the 70 this side.
Oh, never mind. Okay.
Yep.
Yeah.
Yeah, but yeah, that error, that's my fault. So. Okay. Does that make sense? Yes.
Why can't we just look left for that one?
So if we looked left, we would have to consider all of this. We can. No reason not to. We would just have to consider all that. We can't just like say there's nothing going on here. There is. No, it's a great question, but I mean it's an easy mistake to make because there's nothing going on inside the joint right here. So, good question. Sound good? All right. Once you get to this point, the problem should be pretty easy, and let me show you what I mean. And this is really where axial deformations can be ignored. Okay, so let's start off this. Let's just recall that. Those are our properties for this problem, right? It's 30,004 and 8. Okay. So the way that I'm going to organize this is I'm going to do the flexural deformations first, then the axial deformations. So we'll do So the flexural deformations are going to be summing up these integrals. Okay? We're going to be summing up these. Now, how many of them are we going to have? We're going to have technically 2 of them, but so how do we handle that? Well, the first thing I'm going to do is the E and I is constant for the whole thing, and this is a deflection. So I'm going to say 1728 over EI times some integrals. Okay? And what are those integrals? We're going to have we're going to have an integral from 0 to 10 of this plus an integral from 0 to 20 of this. But by the way, what can we do with the first integral? Goes to 0 because that's what we've got. And we know that one's 0, so we don't even have to worry about it. So all we have is 1728 over EI times an integral from 0 to 20 of x minus 20 and 70x minus 1.5 x squared minus 600 dx2. Okay. So let's just sort of digest what's going on here. This is just a regular old calculus problem at this point, right? This is something you can plug into your Casio FX115ES Plus, integrate from 0 to 20, or break out the old Wolfram Alpha. I know college students use that every now and then. So integrate from 0 to 20, multiply by 1728, divide by EI. Are you okay if I just told you what the number was when you do that? Okay, so when you do that, you get plus 3.36. So therefore, if we calculated the deflection at A and all we used were the moments, we would get 3.36 inches down. Does that make sense? How are we doing on that? Okay. Now, for the axial deformations, what I'm going to do is do a truss problem. Remember how we calculate deflections using for trusses? Little f, big F, L over EA. Remember that? So what do we got? We've got little f, AB. Here, let's do it like this. The 1 over EA, that's consistent. So we have little f, big F, L, plus little f, big F, L. But does anybody see something that's going to cancel? Or get eliminated? The second one, right? That's going to be 0. So all we've got is which is, I mean, what do we have? We have 1.0, 10 kips. Remember, AB is 10 feet long, 30,000, and then 4 square inches. Remind me, when we calculated truss deflections, what did we have to do to the member lengths? We had to convert them to inches, right? Y'all remember that when we did virtual work for trusses? We had to take the truss lengths and convert them to inches. So we got to throw a 12 in there. What do we get when we calculate this? We get a value of 0.01. So therefore, we get a really, really small deformation. It's like, think about this. If we were to ignore the axial forces, we would say that the deflection is 3.36 inches. But if we consider the axial forces, it's 3.37. That's like the same deflection. We're talking about structural deformations in buildings and bridges. the percent difference between those calculations is relatively minimal. So what I am saying is that for frame deformations, you can ignore axial. You can ignore it. That's what I'm saying. Okay? Does that make sense? And keep in mind, I said at the beginning, this was a member that was very flimsy axially. Very flimsy axially. Really small area, really big moment of inertia, and it's still barely stretching. Frames just are very stiff axially. They just are. Okay, does that make sense? All right, I would like to make a quick note about shear deformations, though, because remember how I said we could get a shear function, but we didn't use it? Well, let's talk about that. All right, so let's talk about shear deformations. So shear deformations happen when you're considering the effects of the shear forces on the deformation of the structure. Okay? So if a flexural deformation is like that classical bending shape, shear is just that, like a change in angle along the beam. And a lot of times we neglect them. And in most routine structural analyses, we can neglect shear deformations. Now, first off, if you wanted to include them, it's very easy. All you have to do is you just do another virtual work computation. So instead of little m, big M, it's little v, big V. Okay? So you're going to have a big V shear function and a little v shear function, the same idea. Okay? Instead of using the elastic modulus, you use the shear modulus. It's just another lookup value for a given material, and you use the cross-sectional area. Now, when you do the virtual work formulation for shear, there ends up being a lot more cross-sectional terms that show up in your integral. And what we do is we sort of lump that into a new section property, which we call K. But K is a lookup. So, for example, if you had a beam that was a rectangular cross-section, then K is 1.2. If it was a circular cross-section, it's 10/9. Like, you can look them up. It's pretty straightforward. Now, that's how to do it. The big question is, when do shear deformations matter? Okay? More often than not, in building systems and bridge systems, we're trying to use flexural elements that are as slender as possible. And a lot of times, what you're wanting, when I say slender, here's what I mean when I say slender. Okay? So if I have a beam like this, okay, here's a beam. I'm talking about the ratio between this and this. Okay? So I propose that when I'm talking about beam slenderness, essentially what I'm talking about is the L/D ratio. Okay? And more often than not, beams in buildings are fairly slender. Like the beams in this building are probably having an L/D of like 25 to 30, something like that. Okay? And in most applications, an L/D of 25 or 30 is about what you're going to see. But there are some instances where you see a really, really deep beam. Okay? So when shear deformations start to matter is when the beams get deep. So some examples of deep beams would be, for example, in a bridge, if you have like a hammerhead pier. This is a really, really short cantilevered beam that is subjected to a lot of shear. So that section is really, really deep compared to how long it is. Okay, so that's an example of a deep beam. Another example of a deep beam is a transfer girder. So like if you've been in a hotel, there's rooms on floor, but that lobby might span a couple of different floors, so there might be one beam that's having to hold up a lot of force for the building. So you have this one element in the building that's subjected to a lot of shear, so it ends up being really, really deep. Okay? So whenever you have a really deep element, you have to consider shear deformations. So to sort of explain how this can happen, I just want to show you I'm going to walk you through a really, really brief example. So let's say you have a simply supported beam with a uniformly distributed load. The beam is 25 feet long with 3 kips per foot. Okay? It's made out of steel, so this is the Young's modulus for steel, this is the shear modulus for steel. They're just lookups for the cross section. Let's say I start changing the shape that I use. So for example, again, we're going to use this expression. You all can derive moment functions and shear functions. Here they are. Okay, here they are. All right, so if I use a W14 by 26, that means it's about 14 inches deep. So the L/D is about like 21 or so. So here's the area, here's the moment of inertia. If you go through and calculate the flexural deformation, you get that. And you calculate the shear deformation, you get like that. So it's a really, really small value. It's only about 1.9% difference. So for a relatively slender beam, you can kind of ignore your shear deformations. But what happens when the beam starts to get deeper? And I'll skip to the end. What happens if you have like a W36 by 135? This is a really, really deep beam compared to the span. Now, I'm making the beam bigger, right? So if you look at the deformations, they are getting smaller. But if you compare the two, like you're getting about like a 10% error. So if you ignore the shear deformations, that's fine if the beam is slender. But if it's deep, you're going to have error in your calculations. An error between what you're calculating versus what is actually happening in the real world. And the rough idea is if your L over D is less than 10, you need to include shear deformations. That's when it really starts to matter in most applications. Sound good? Come prepared with questions on Friday. That's all I got, everybody.